Great. Geophysical.
Good morning, everyone. My name is AGLYao. I work with Dr. in the Geophysical Lab, and I'm also a part-time student still working on my PhD degree on geophysics. So today I'm going to talk about a low frequency measurement system recently developed in our lab. Okay, it works. You can stand in front of this group of audience. I don't think I need to stress why it is important to do the low frequency measurement. Just two things, dispersion and attenuation. We need to know more about dispersion and attenuation. For example, dispersion. If I raise a question, what is dispersion? Probably everyone will raise hand. If I ask why there is dispersion in sedimentary rock, maybe 60%, 70% person will raise hand. But if we go to the real application-oriented, ask where is the dispersion, how much dispersion there, can we quantitatively relate the dispersion to a particular rock? I don't know how much people can raise the hand with confidence. And a similar situation to the attenuation. People have noticed that the relationship kind of attenuation can be related to the partial gas saturation, partial water saturation. But if we again go to the real application, we want to quantitatively relate how much attenuation can be associated with how much gas partial saturation. Then that's a problem. That's why we need to do more logical work to quantitatively relate them. A little bit about history of the lab measurement. As Jose just mentioned earlier, we normally use the ultrasonic. That's the post-transmission method directly measure the wave velocity. But that's in the megahertz frequency. And back in 1980s, a bunch of experiments to try to go to the low frequency using the technique of resonance bar. And a couple of limitations, most important of them, this method has the lowest frequency goes to never below 400 hertz. So it doesn't really goes to the seismic frequency. So finally it comes with another new technique, it's the force deformation method. With this technique, we can really measure to the frequency of in the seismic band, which is a couple of hertz, goes to a couple of thousand hertz. So what's the principle of this force deformation method? Actually, we don't directly measure the velocity. We measure the elastic constant. What we do is we apply, this is the sample column, we apply a sinusoid stress field longitudinally to this sample. Then we just measure what's the induced strain. Then use the stress-strain relationship, we can find out what's the elastic modulus. And this is the schematic drawing. This is the real system here. You can see this is the source of the stress. It's a shaker, we call it. Then we have the sample here. We just press the sample and put the strain gauge on the surface of the sample and measure the induced strain. Then a little bit detail about how to get the elastic modulus and attenuation. Normally we have to put multiple strain gauges with both at the vertical direction and horizontal direction. The vertical one will measure the Young's modulus, and the horizontal one, along with the vertical one, will measure the Poisson ratio. Then assume it is isotropic material, we can get all other elastic modulus like bulk modulus, shear modulus. Then we can calculate the velocity from that. And for attenuation, we just need to measure the phase, because this strain output not only gives the amplitude, we can also measure its phase. So by look at the phase difference between the stress and the strain, we can calculate the attenuation. And this is the theoretical principle, but for the practical reason, we actually do not really measure the stress because the stress is much difficult to measure compared with strain. What we do is, along with the sample, we put another pieces of material with no well-known property, and we also measure the strain output from that. We call it standard material. We just because with this kind of configuration, it is under the iso stress condition. That means the stress everywhere is the same. We just need to compare the strain output from the standard material and our sample. Then we can relatively calculate the Young's modulus Poisson ratio of our sample. So here is the detail. Like this is the sample here. I just put a piece of glass, plastic glass, or put multiple strain gauges on that, and then do a measurement. And below here is the standard, which is aluminum, with the well-known property. So it seems that the physical principle is quite simple and straightforward, but actually to carry out this measurement, the engineering challenge is very high. And at its center, it comes with this requirement, because we are trying to look at the dynamic property. It's not just static property. To mimic the far-field seismic field amplitude, it has to be controlled with the strain to below 10 to the minus 6. And the consequences of this requirement is the strain output from all the electronics is also very small. It's in the range of microvolt. And we know in today's environment, we are full of the electromagnetic noise, and this noise level can be easily goes to 10,000 times our signal. It's in the millivolt, and our signal is microvolt. And the result of my measurement is very sensitive both to both the amplitude and the phase. So we have to take a lot of special cares, both on the hardware and the software. And I will go into a little bit of detail about those and the sample. And finally, to get a robust result, we have to carry out multiple calibrations at a different level to make sure we got the trustable result. First, I need to acknowledge we are, we have learned a lot from both the school mine and the shell company. They have developed a similar system that we learned a lot from them. We acknowledge here, but we add a lot of new stuff into that. We are not just simply copy their design, their system. For example, mechanically, instead of their system, we put the sample assembly here. As I mentioned, the standard material, my sample here, stationary. Not like the school mine system. They will move it after install all those samples, strain gauges. They have to hand it into the pressure vessel. But our system is have all this stuff stationary. We don't have to move it after install it. So because this measurement mechanically is very sensitive, so we need high reliability. So we change the design to make it stationary. After everything connected, we will never move it. This is one thing. And again, different with the shell system, they have the similar kind of stationary assembly here, but their shaker is outside from the pressure vessel. They use a rod to transfer the stress field into the sample. But we put the shaker, everything inside sample very close to my sample. So in this way, we can have better control on the vibration mode, because this is also very critical to get the right result mechanically. And electronically, a lot of things, because as I mentioned, the signal is so small, the noise is so high, so we have to develop something very special. We can't get from the market like this is a small signal amplifier, but a lot of different features to that to make sure it can amplify my very weak signal. And every detail, how to show that, how to connect everything, This is the overall instrument here. And one special thing is for this kind of the very, very low signal noise ratio, we have to use the locking amplifier try to retrieve the signal out from the noise. And this is quite busy figure here, but the principle of the locking amplifier, actually we can think about it this way. It's just a very, very narrow band Fourier transform. For Fourier transform, we can get both the amplitude and phase information for any frequency in the Fourier transform frequency range. But here, we don't care about all the other frequencies. We only care about the frequency we apply to the sample. So we can simplify its process. And this is normally accomplished by a standalone equipment manufactured by vendors like Stanford Research. But here, we closely worked with National Instrument to develop a virtual, we call it a virtual locking amplifier, which is a completely software version locking amplifier. This is the first one in the world put into work condition. And the main advantage of this virtual locking amplifier compared with the hardware locking amplifier is here we can separate the locking amplifier process completely with the acquisition hardware. So by this, we have the flexibility to choose the best acquisition hardware in the world. For example, we choose a National Instrument acquisition board which has 16 channels and which has 24-bit vertical resolution. What does that mean? 24-bit means that if you have a signal input range from minus to plus 10 volt, then this 24-bit means that you have the minimum resolution to 37 nanovolt. If we recall, our signal range is in the microvolt. Then this, 37 nanovolt can provide the necessary resolution. And also with this kind of design, we have better integration with the processing after acquisition. Then also we developed our own software package for the acquisition, processing, and automation all together. I have a very, very short video here. We can show how it works. Here in the center, this is the monitor of the strain gauge output. We can see it's quite clear, quite stable sine output here. The blink here actually is changing the frequency because we have to scan from like 2 Hertz to 2000 Hertz every time it changes. And these indicators just show the output real time. And here I also put, okay, we can look at how it changes from one frequency to the next. 796 and goes to the next frequency. Then after it finishes acquisition from one frequency, immediately we can calculate the amplitude, Young's modulus, Poisson ratio, phase difference, and display immediately. So it's a real-time system. And calibration. Because we have multiple channels, we have to do very careful calibration to make sure this is before calibration, and after calibration we can see we can put all the signals together to each other. That means with a very high consistency between channels. So here's a picture of the whole system, and this is just one of the results we obtained from rare sandstone. This is the dry measurement, and the brine butane saturation. We can see the different situation. Dry, we don't see much attenuation. With the butane saturation, we can see clear dispersion here, and also the Q value displayed here. So that's all I need to show, and we have to acknowledge the support, financial support from the Fluid Consortium.